There we go. Okay, now I'm recording. Okay, so again, a reminder that a watt is joule per second. And you remember that joule is a unit of energy. You guys used that when we were calculating potential energy and kinetic energy. They're all joules. So here it is, joules per second is a watt. Okay, so down here, you guys already discovered from your homework that power is current times the voltage, or we say change in potential. That's why there's a delta there. So here we go. Voltage, that's volt, and current is amperes. Amperes, which we just say amps for short, and we use capital A. And what's an amp? An amp is a coulomb per second. A coulomb per second is an amp. We already said volts, hopefully you guys remember from the homework earlier, is joules per coulomb. That's a volt, joules per coulomb. So our coulombs cancels out and we end up with joules per second, which is a watt. All right, so before I get to this example here, I wanted to go back to the chapter outline. Some of you guys who've been watching the videos, I made a two-page, two-sided outline, and it's called chapter 16, 17, and 18. All right, so let me go through that really quickly. I gotta do stop share and then move over to my table. Okay, go to my table here. All right, so this I attached on a couple of your homeworks already. So since it's all related, I just made a worksheet for you, a summary page of chapters 16, 17, and 18. So there it is. You guys did homework on the electric force, electrostatic force. We already talked about this in class, all the different types of work. Here's some of what we did on the homework in chapter 17. And on the back side, you've got really the end of chapter 17 and then chapter 18. Okay, so you already did, that is the charge over time, that's current. Okay, and here are the units. For current, the units are amperes. For resistance, it's ohms. And for potential difference or voltage, it's volts. And there it is, joules per coulomb. Resistance is volts per amps, volts per ampere of current. And then coulombs per second is current. Okay, so here's another big sort of summary. What we've got now, capacitance is farads, and then here's the actual what it looks like, resistance, ohms, and W for watts. All right, so here's a reminder. V equals IR. It's one of the things I have memorized if you woke me up in the middle of the night. Quick, what's the equation for voltage? Current times resistance. All right, so this is what I'm going to go through on the outline, and then here's a summary here of your resistors in series and your resistors in parallel. Okay, and here's all the different versions of just V equals IR and P equals IV. Those are the only two I have memorized. Then I just derive the other ones as I need them. But I thought that was a kind of cool way. These are all expressions for power, upper right-hand corner expressions for voltage, lower right-hand corner expressions for resistance, and the lower left-hand corner expressions for current. Okay, let me go back to my outline. I think I would know this by now, but no. Okay, here we go. Oh, I guess I could have stayed with the one on my, I just want to remind you guys about that outline that I had made for you. Okay, so here's our first circuit of the day here. This one you can see. I wanted you guys to see there's different ways of representing the battery. For me, it's easier just to do the plus minus inside of a circle, but you do want to understand this one. So this one could be two batteries in series. The longer one, the longer line means the positive terminal of your battery. And the shorter one is the negative terminal. Okay, so you might want to write a plus on this side here and a minus on this side here. So I have a 9-volt battery connected in parallel to 10 ohms of resistor, 10 ohms resistor. And I say parallel because they both share 2 nodes. So this side of the resistor is shared with this side of the battery. This side of the battery, the negative terminal, is shared with this side of the resistor. Okay, they're in parallel. So what do we have here? We have P equals IV. Well, I know what the V is. I got the voltage, and I know what the resistance is. I've got 10 ohms. So how do I figure out the power? All right, so here's what you got to know. P equals IV. Well, I know that V equals IR. So if I replace this V with IR, then I have I times R. Are you guys with me? I, and here's the other, the V is IR. So that's why it's I squared R. Okay. I wish I had maybe a better font that has the, there we go. Well, doesn't mean to be pop. Well, anyway, I think you guys are trying to say, I'm just trying to show you that's an I there. Came out too fat. The elephant is too fat. How about Harrington? Okay, a little better. All right, so then why is it that it's also V squared over R? Well, let's go back over to this box here. If V equals IR, then hopefully you see that I is V over R. Well, if that's the case, I'm going to go back to IV here, okay? I know that the I is V over R. So let's replace this I with V over R. So I have V times V, here's the other V, divided by R. And that's why it's V squared over R. You guys with me? All right, so the power here I can figure out by taking 9 volts, squaring it, and then dividing it by the resistance. And that would be 9 times 9 is 81, and 81 divided by 10 is just 8.1 watts. There we go. All right, so that's a review of simple equations. To me, all you need to know is P equals IV and V equals IR, and then you can derive these. Make sure you get these though. In your cases, you guys, all your tests are open book. But I want you to understand why it is I squared R and V squared over R. Okay, any questions? All right, before we get to the power meters, I wanted to show you guys a short little video. Let's see, I have it ready. This one here, now I need to say share screen, stop share, share screen, there we go. Okay, so we're going to talk about energy and then power. Okay, you guys can see that?
What changes in electrical potential energy would take place in this circuit if it were closed?
All right, so why is it an open circuit? You'll notice that this little connector, they're called alligator clips, is connected to this side of the battery. The other side is connected to this light bulb, which the connection is over here. So I've got this little wire connected, and the other side of the light bulb is connected to B. That one's connected to this alligator clip, which is not yet connected to the battery. I'm going to replay that.
What changes in electrical potential energy would take place in this circuit if it were closed?
Okay, now we're going to connect it to the battery.
When the circuit is closed, charges move from one terminal of the battery to the light bulb. Ignoring very small losses in energy in the connecting wires, there is no change in potential energy in this part of the circuit.
Okay, so the potential energy stays the same.
When the charges move through the filament of the bulb, they encounter high resistance. The charges lose electrical potential energy as they collide with the atoms of the filament. The electrical energy is converted into internal energy, and the temperature of the filament increases.
Okay.
When the charges reach the other terminal of the battery, their potential energy is 0. For the charges to move from the second terminal to the first, they have to gain energy. This is provided by the chemical energy of the battery. The process goes on continuously until the chemical energy of the battery is exhausted.
So your battery will run down eventually.
The electric power of this circuit is the rate at which charges lose electrical potential energy. Numerically, this is equal to the current flowing through the circuit times the potential difference.
All right, so just remember, potential difference is another way of saying the voltage. So looking at this battery, A and D are the terminals. Across A and D, there's a voltage drop equal to the amount of volts of this battery. So maybe this is a 3-volt battery. So I've got 3 volts across A and D, which by the way, will be also across B and C. What do I mean by across? If you had your multimeter, you put 1 lead on C and 1 lead on B, you'll get the same amount of voltage that if you did over on one on A and one on D. All right, any questions? Okay, one more short video. Let me go grab it. Ahí está. Now I gotta go say share screen again. Okay, you guys can see that? Okay, so this is an example of the power meter outside your house, apartment complex, etc. Each of your apartments should have its own so that you're only paying electricity that you've used and you're not helping to pay for your neighbor's electricity bill.
Power companies charge for the amount of energy that a customer consumes during a specific period of time, usually about a month. The kilowatt hour is a unit commonly used by electric utilities to express that energy consumption. We can convert kilowatt hours directly to the more common energy unit of joules. We'll begin with 1 kilowatt hour. We convert kilowatts into watts by multiplying by 1,000 watts over 1 kilowatt. Next, we can convert hours into minutes by multiplying by 60 minutes over 1 hour. We convert minutes into seconds in a similar fashion, multiplying by 60 seconds over 1 minute. If we pause to take a look at our units, we see that we can eliminate kilowatts, hours, and minutes, which leaves us with units of watt, seconds. Performing the multiplication, we find that 1 kilowatt hour is equal to 3.6 times 10 to the 6th watt seconds. The definition of a watt is 1 joule per second. If we express the units in this way, we see that the watt second is the equivalent of a joule. Therefore, 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules.
Okay, any questions? Just a good review for you on dimensional analysis here. All she did was she converted what a kilowatt hour is, because that's how those meters are reading how much electricity you're using, kilowatts. But we're used to joules for how much energy that is. So 1 kilowatt hour, meaning you used up a whole kilowatt in an hour's time, is equal to 3.6 times 10 to the 6 joules. That's a lot of joules, right? 3.36 and then 5 more zeros after that. Okay, so a megajoule, 3.6 megajoules. They don't say that, they just say joules. All right, so let me go back to my outline. I guess I got to say it again. Share screen, outline. All right, so I want somebody to tell me if they have recognized any of these power meters outside their house or apartments section. Anybody seen something like this? This one to the farthest left, maybe I'll make it bigger for you. The one the farthest left is digital. How do I know that? Because it's a digital reading. Okay. If you guys remember, maybe don't, it took a long time before they actually came up with technology for digital. So everything was analog. So most houses, I would say in the country, you guys can see this one, are still analog. You can see the words kilowatt hours. So look outside your apartment, somewhere outside usually. And then what happened was there were meter readers. Yeah, somebody had to come read your meter. And they would do this every couple months. I think we get billed maybe quarterly, every 3 months we get a bill. So look, they circle here how many total kilowatt hours. So here's all the dials, and then they finally get it into an analog number here. Okay, and then I wanted you guys to see one kind of zoomed out. So here's another example of one. They're usually a silverish kind of gray cabinet, and you can see a pipe connected to it. Okay, any questions? So that's your home power meter. This is how your mom or dad is well, they're responsible for paying for the electricity that you are using, okay? Your lights, your appliances, etc. Okay, and as she explained, 1 kilowatt hour is 3.6 times 10 to the 6 joules. Yes, this is good for you to have written down somewhere, okay? Before we move on to the worksheet, I wanted to really stress how much I really encourage, and I hope you guys will take notes on these particular videos. I think they do a really good job. And the, I'm trying to say here, the graphics are really well done, explaining on the electric fields, which hopefully gives you a better understanding for what's happening in electricity, and then the voltage, electrical energy, and capacitors, which then gets you to electric current, particularly the analogy of electric current to water, flow of water. There's an analogy that can be made there, as well as resistance. Resistance would be something that would impede the flow of the water. Okay, and then DC resistors and batteries, simple circuits, and then series and parallel, which we're going to start on Monday. Okay, and then series and parallel circuit analysis. And I already did the star videos for that as well. But I really want to encourage you guys, make sure you watch them. And they're all around 10 minutes or so. I also gave you guys in the Google Classroom some other ones that I think are good because they actually show some real examples that I would have been doing if we were in class every day together. Okay, any questions? So let's move to the, and I do want to know if you have any questions, but I'm going to move over to the worksheet on my table. But please let me know if you have any questions so far. Okay, here we go. Let's start with this worksheet here. So this worksheet I like because it's going to be kind of a summary and hopefully putting together for you guys what we're talking about here. Okay, the first one, and I'm going to use my list here of people. Blank is a word to describe the flow of positive charges. Notice that. Positive charges, there's nothing positive that's moving. It's the electrons that are moving. So electrons are going in the opposite direction of what the current is. So, oops, I just accidentally said it. So Carlos, what is the word to describe the flow of positive charges, even though there's no such thing?
Is it current?
Yes, sirree, Bob, good job, current. So just the term, the standard is called current, but there is no positive charges that are moving. So really current is in the opposite direction of the flow of electrons, but they got to name it first, I guess, and so it stayed. Okay, all right, good. Now, what is the term to describe energy for charged particles? I'll give that to you. That was our homework in chapter 17, and that's coulombs. Coulombs. Coulombs is a term to describe energy for charged particles. All right, now, here's something I want you guys to learn if you haven't learned this already today, is in a parallel circuit, what is always the same? Each is used, the electrical component is the same, parallel circuit. But in a series circuit, through what through each electrical component is the same. So here, I'm going to go ahead and tell you. I wish I had with me a little multimeter. Here's my little, let me grab a pencil instead. Little multimeter. Here's my little multimeter. And I'm going to take, and I'm measuring voltage. And I take one right here and one right here. Why did I pick the middle? The E resistor and the C resistor are in parallel. Notice that this node here is the same as this node here, which is the same as this node here. And on this side, this node here is the same as this node here, is the same as this node here. They're in parallel. So it turns out that the voltage is going to be the same if you measured it on either side of the E resistor and on either side of the C resistor. Okay, so in a parallel circuit, the voltage, and I don't like the word use, please fix that. Let me use a pen here. It should say across. Should not be used by, across. So what I want you guys to imagine, see if I can draw, I'm not the best artist here. I'm going to make one resistor here. I'll call this the E one, and I'm going to do the C one right here. Imagine it like this. I didn't draw straight lines. I didn't make them into like little boxes, but you see that they're connected in the same place. The C resistor, should have made it bigger, and the E resistor. Okay, those are called parallel. So by definition, when you have elements that are parallel to each other, I say elements because it could be a capacitor. Okay, it could be an inductor. But if I have them connected in parallel, then the voltage across them is the same. Okay, any questions on that? Now, on the flip side, current, notice this A and B resistor. It turns out that the current going into this A resistor, which comes out of this A resistor, current doesn't change. Then the current goes into the B resistor, and then it comes out of the B resistor. The current doesn't change. So in a series resistor, the current through each electrical component is the same. Okay, the current doesn't change. And by the way, I'm putting I because that's what we call current. Look what happens when the current gets to this point right here, it splits. Some of it's going to go up and some of it's going to go some of it's going to go up through the E resistor and some of it's going to go through the C resistor. Okay? So the E resistor current continues here, it comes down, and it's going to add with this resistor. When they add up together, it will be the same as when it came in. What do I mean? If it was 5 amps coming at this point, and these guys were exact same resistance, half of it would go up through here, half of it would go through there, then they add up together, and they add up back to I, whatever I was. Okay? Then that current is going to go through the battery and back up through resistor A. Okay, any questions? This is a really important concept that elements connected in parallel, the voltage will be the same. But elements connected in series, the current will be the same. The voltage will not necessarily be the same. Why? Because V is equal to IR. So if the R is different here, RA and RB, then the voltage is not going to be the same. Okay, so the current stays the same, but the voltage isn't. Any questions? I'm going to pick the next person on my list. Iris, tell me what's the difference between elements that are in parallel and elements that are in series, please. You have to unmute yourself though. Are you there, Iris? Okay, I'm assuming everybody's still here. All right, Iris isn't there. Jeremy, can you help her?
In a parallel circuit, the voltage is the same, while in the series circuit, the current is the same.
Exactly, exactly. Okay, muy bien. All right, so let's look at the next one. Number 4. For the circuit at the right, alphabetically list the resistors that are in series. Okay, so, oops, I got a chat here. So I'm going to ask Luis. Oh, okay, thank you for telling me. Thank you, I appreciate it.
Would it be A, B, C, D?
Okay, wait a minute. Whoa, A and B are definitely in series. Okay, they're definitely in series. So that's correct. A and B. C is not in series. And why is that? Because we have something else hanging off of it. We have something else hanging off of it. So B and C are not in series because there's something stuck in the middle. Are you with me?
Yeah, and that would be E,
What you
right?
can say though, and you're going to learn, is that E and C, you're going to learn about the parallel combination. There's a way to find the equivalent resistor of E and C. And that equivalent resistance, that's in series with B. Okay, but it's not in series with C right now or with E. Okay, everybody got that? And the reason why D is not in series with A is because there's something actually between them, a battery. Okay, so A and B share a node. Okay, B and C look like they are, but they don't because there's somebody else stuck to it. Okay, everybody got that? All right, muy bien, muy bien. Josue, number 5. In this circuit here, which resistors are in parallel to each other?
Wouldn't it be E and C? No, wait, yeah, E and C.
A and C, muy bien. E and C. Okay, muy bien. All right, good. Now in this next one, this next circuit, I like it to show you that, yeah, sometimes you're not gonna see it all perfectly, all drawn just as little line. It could be what the circuit actually looks like. Remember I had all those, my connectors, the banana clips were kind of long. When I was showing you the capacitor charging circuit, they're kind of really long and I had them kind of wrapped around in some rubber band. So this long thing, we're assuming that the wire itself has no resistance. So you have to use your imagination and go, so I can ignore all this and just kind of shorten it all up. Okay, if I can shorten this all up, then this would look like, okay, I'm going to use it 12 volts. Here's my 12 volt on the bottom. Okay, and I'm going to write it like it's doing right here. Here's a 2 ohm. There's 2 ohm. I'm following this all along and I'm like, oh, look, it's in series with the 4 ohms. It's in series with the 4 ohms. And the other side of the 4 ohms connects with the other side of the battery, huh? I want to make sure, does everybody see that? You see that? Let me see. Josue, explain to me why I can redraw this circuit like that.
Because wouldn't the current, like, it would still go like
Yeah,
the
that's a
same?
great way to explain it because the current is not going to change. That's exactly another good way to explain it. The current is not going to change. Okay, good. Now, since we got Josue, what is the total resistance? Now, what do I mean by that? This battery, it doesn't know how many resistors are connected to it, how many are in series, how many, it just sees one equivalent resistance. That's all it sees. And hopefully you guys have your, I'm looking for it here, the what am I calling this? Outline page. I should have called it summary page. Okay. When you have resistors in series, all you have to do to find the equivalent or the total resistance is add them up. So Josue, in this circuit now, what is the equivalent resistance?
6?
Yes, it is. How did he know that? Okay, so this nice battery here, it only sees one equivalent resistance. I'm going to call R equivalent or R total. That's supposed to be connected, okay? There we go. And he realized these are in series and 2 plus 4 is just 6. 6 ohms. Okay, muy bien. So that one is 6 ohms. Okay, because they're just in series. Okay, muy bien. Let's see, moving down. All right, this one gets more fun. Stop me if you guys have questions. The next one, which is covered in green. I don't know why. Probably when I copied it from wherever I got it. All right, the next one. What is the total resistance for the circuit at the right? This one right here. So let's see, I've got Juan Diego, you're up. I have a 24 volt battery. Oh, the negatives on the top and the positives on the bottom. And I have these resistors in a very interesting configuration. How would you describe these resistors? What do you think? Do you think they're in series? Do you think they're in parallel?
Aren't they in parallel?
Yes, they are. Good job. How did he know they're in parallel? Well, he noticed that this is the same node for this 3 ohm resistor, and this is the same node for this 6 ohm resistor. And he noticed that there's nothing between these two other than just wire. So I could just shorten these up, and make it look like what you're used to for parallel. See if I can do that here. I'm going to do a 24 volt, and I have one resistor, and I have another resistor. Okay, you're right. This is a 3 ohms, and this is 6 ohms. They are in parallel. Everybody needs to see this. I mean, visualize that these two I can shorten, squish up, and I can represent it like this. Now, I don't have to represent it like that. I could represent it like this one here, except it would be in this orientation. But he recognized that they're in parallel. Muy bien. So, do you remember, or have you learned yet, what is the total resistance here? Remember, this battery only sees one resistance. So, I'm going to say this is like a 24 volt battery. Oops. All right. And only one resistance, the equivalent resistance. So, we go back to our, I'm looking for my, here it is, my summary page for the chapter, and here it is. When you have resistors in parallel, the inverse of the total resistance, or I like to say equivalent resistance, you could say equivalent resistance, is equal to the sum of the reciprocal of each of these resistors. Okay, so Juan Pablo, on this one here, how would we determine 1 over R equal, or 1 over R equivalent? What's that equal to?
Wouldn't that equal 1/3 plus 1/6?
Muy bien! Ding, 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 ding. 1/3 plus 1/6. Now, yes, you could use your calculator, but I happen to know that 1/3 is equal to 2 6s, right? That's 2 6s, right? 2 6s plus 1 6. And 2 6 plus 1 6 is equal to 3 6. So what's our equivalent then? Juan Diego.
I said 1/2.
Oh, wait a minute, wait. See how 1 over R equivalent is 3 6s? So I want to flip over 1 over R of a Q to get what R of a Q is. So I have 3, 6. So what's the flip of 3 sixes?
It's 2.
6 thirds. Oh, so that's why he said 2. Yes. So it's 2 ohms. Muy bien. It's 2 ohms. Okay, so the total resistance when you have a 3 ohm resistor and a 6 ohm resistor is 2 ohms. Okay, and you figured that out because 1 over our equivalent is equal to 1 over 2 plus 1 or 1 over 3 rather ohms plus 1 over 6. Okay, muy bien. Now, every time you have resistors in parallel, the total resistance will be less than the smallest resistor. So notice how we have 6 and 3, and the equivalent resistance was smaller than 3, is less than 3, because here it's 2. Okay, muy bien, Juan Pablo. All right, you're going to rock on the parallel stuff. All right, here we go. By definition, the rate of flow, who's next on my list here? Cristobal. So Cristobal, what do you say? The rate of flow of electric charge is called, what does that mean when you've got electric charge flowing through a circuit?
Would it be current?
Yes, sir. Muy bien. It's current. Muy bien. And what's the units it's measured in?
Amps?
That's right. Amps. And then the actual word is ampere. Well, it's French, ampere, but we just say amps for short. Okay, we just say amps. Okay, muy bien. All right, now here we go. We're gonna actually start solving some circuits. But that was too easy, so maybe we'll have Cristobal continue, huh? Because this is too much fun. All right, so here we go. We're gonna start with number 9 here. How am I doing on time? Good. Number 9. Okay, so question here. I've got a resistor here, but I don't know how much resistance it is. And I have another resistor here, and I don't know how much resistance. And yes, they are connected in series. I see that. And they're telling me that I have 9 volts across this one. Oh, and look at that. They're telling me that the current through this one is 2 amps. And they tell me the battery is 12 volts. Okay, so I'm going to go ahead. I like using the plus minus so I can see what I'm doing. So between here and here, if I were to take my voltmeter, I'm going to get 12 volts because it's parallel to the battery. So from here to here, I have a 12 volts because that's the same thing as from here to here. Well, that means whatever the voltage is across this guy here, plus the voltage across this, has to be equal to 12 volts. Okay, again, the battery is supplying the voltage to the whole circuit. That's all I got. I got 12 volts. How you want to use it, it doesn't care. It told me that I'm going to go ahead and put down the plus minus here. It dropped 9 volts across this resistor. So how much do I have left across here, Cristobal?
You would have 3.
You had 3, and how did you know that?
Subtracting 12.
Exactly. Okay, so I'm going to say here 12 minus 9 is 3 volts. Okay, so you have to look at the circuit and say, okay, I've got 12 volts to play with. I already used up 9 of them here, so I only have 3 left. Okay, muy bien, muy bien. All right, let's let someone else have some fun. Andrea, so I know that I have 2 amps going through this resistor. How much current is going through this resistor? Remember, they're in series.
2 amps because...
Yes, ma'am. Good job. How did she know? Well, she remembered up here. We wrote down somewhere here, that when they're in series, the current is going to be the same. So she knew, good job, she knew that if I have 2 amps going through here, then I obviously have 2 amps going through that resistor as well. Okay, good job. Now, it wants to know what the power is. The power is of the circuit. Well, if I have 2 amps going through here, I have 2 amps going through here. Well, guess what? I also have 2 amps going through the battery. It's going all the way around the circuit. All right, and I know that the power is just the current times the voltage. Yeah. So how much power does this battery actually supply to the circuit? Well, right now, because I have 2 amps, and I have 12 volts, I'm going to have 2 times 12, which is 24 watts. Are you guys good? Any questions? All right, now let's take a look at a parallel configuration. Here we go, parallel. Let me see. Should we give Andrea more fun? All right, here we go, Andrea. Yeah, let's give Andrea more fun here. Okay, so Andrea, I don't know what the voltage is of my power supply or my battery. Don't know, but it looks like 10 volts is across this resistor. Oh, do you know then how much must be across this battery?
It would also be 10.
Muy bien. Yes, Reba. Good job. It's also 10 volts because they're in parallel. And as we discussed up here, in a parallel circuit, voltage across each electrical component is the same. Okay, so she's right. So she knew there's 10 volts across this resistor. Therefore, I must have 10 volts on this power supply, which, by the way, what's the V2 then, Andrea?
Also 10.
Also 10 volts. Muy bien. Okay, it's also 10 volts. Okay, good job. Good job. Let's see, moving down here. Looking here on my list. I got lost on my list. Yasmin, here we go. Yasmin, so I have 6 amps going in through the battery. So that means that coming into the battery is 6 amps. But I noticed that when it comes here, it splits off. Some of it's going to go this way and some of it's going to go that way. So if I have 6 amps coming into this node right here and 2 amps branches off this way, how much current is going through this top resistor? Are you with me, Yasmin? Okay, I lost Yasmin. Let's see. Brianna, can you help?
I'm not sure.
Okay, let's look at it again. Brianna, I got 6 amps going in here. 6 amps is going in here, 6 amps. And then 2 splits off this way. So how much is left over to be able to go up here?
Oh, okay. 4?
There you go. She goes, I know 6 amps minus 2 amps is equal to 4 amps. Okay, so I got 4 amps going through this resistor up here. And this is why the water works analogy. Some water is going this way. And by the way, this happens in fluid dynamics too. Some is going to be this way and some is going to be diverted that way. But when they come together, if I have 4 amps here, you figured out, 4 amps here, 2 amps goes through here, add them up, 2 amps goes through. When they come back together to this node, they add up and they add up to 6 amps. And that's what goes through this battery. Okay, so what's the power? Okay, power is IV. Going through this battery, I have a current of 6 amps, and the battery is 10 volts. So who's next here? So Brianna, so what's the power then delivered to the circuit?
It would be 6 amps times 10 volts. So
right? What's the units for power?
Watts.
Correct. Okay. Congratulations, you guys. That was the first side of the page. I think everything's going to be easier now. So I'm going to summarize for you guys on this one, on this side here. So it's just really the pivotal core. Understanding we have a series circuit here. Important in the series circuit, the current is the same. Here we have a parallel circuit. So we know the voltage across each of these elements, because they're sharing nodes, is going to be the same. And then we realize, oh, 6 amps coming into this node, 2 went off of it, so it must be 4 left over to continue through this top. Okay? And sure enough, we've got 4 amps. And, oh, by the way, now we can figure out the resistance. Let's call this R1, and here's R2. Now I can figure out the resistance, how much it is. Let's see, I've got V is equal to IR. So R is equal to V over R. So I have 10 volts here divided by, I'm sorry, R is, okay, V over I. Sorry, V over I. There we go. So I got 10 volts divided by 4 amps, 10 fourths. So it's 10 fourths ohms. What, oh, sorry, you guys can hear that. 10 fourths is 2.5. So that's 2.5 ohms, right? 8. Did I do that right? 10 divided by 4? Any questions on that? Checking my math here. 2.5. All right, what about this one here? Again, it's V over I. I got the voltage as 10 volts divided by I is 2. 10 divided by 2, I got 5 ohms. So this one's 5 ohms. So now we solved everything about this circuit with the little information they gave us. Any questions? Let's go to the back side of the page. Well, I wasn't able to. All right, here we go. Multiple choice. Let me see. Moving down the list here. Are you back, Yasmin? Give you another chance? No? No answer from Yasmin. Okay. All right, let's see. Dayanara, number 11. You're up. In the circuit above, what is the current going through the 2 ohm resistor? They want to know how much current is going through here, which is not the same thing as the current going through there. So Dayanara, first of all, how are these resistors connected? Okay, you guys know that I have to take points off when you're not there, huh? Okay, so Dayanara's not there. Okay, what about Kimberly? Kimberly, how are these resistors connected?
They are parallel.
Correct. So what do you know about parallel right away? What do you know about parallel?
We would have to use the same equation we did in number
What
7.
is the same when it's parallel?
Oh, the voltage.
Correct. So if it's 10 volts, here's plus minus. If it's 10 volts here, I know it's 10 volts here. And I know it's 10 volts here. Correct? So I know it's 10 volts here also. Okay. Now, if V is equal to IR, and they want to know what I is equal to V over R. I know the voltage here is 10 volts. 10 volts, and I'm going to divide it by the 2 ohm resistor. So, Kimberly, what's the current? Kimberly? Oh, shoot. Did I lose Kimberly?
Yeah, I'm sorry. So
10 volts divided by 2.
It would get 5, so B.
Exactly, 5 amps. Muy bien. Okay, and then you do the same thing if you needed to know the current going through this guy here, except you'd put 6 ohms down here. And then you can add up those 2 currents to figure out how much was coming out of the battery. Okay, you guys with me? Okay, Sergio, you're up. Here we go. How much power is dissipated by the resistor in the circuit shown above? There's mine. All right, so Sergio, what equation do you know for power?
It's just
Where's my summary page here? Here we go. You got a couple choices. IV, that's the one I have memorized. And these I always have to derive from this one right here. Okay, P is IV. If I replace the V with IR, then I've got I times R. That's the I squared R1. Okay. And if I replace the R, IV. Okay, and then I've replaced, anyway, you're with me, V squared over R. Okay, so tell me now, what is power equal to? IV. It helps if you guys write this stuff down and should be taking notes. All right, so let's see. I've got the voltage, that gives me the V, and they got the resistance, gives me the R. So I'm going to take one of these that I already, you could do this in 2 steps if you want, but you don't have to. I got V squared over R. Okay, V squared over R. So now how do I solve that, Sergio? What do I plug in?
you put the 100 squared over.
Good. 100 squared over 200.
200.
Good. All right. So I know that 100 squared, you know what that is? 100 times 100 all over 200. That's how I do it. I always try to avoid my calculator. All right. So 2 zeros get cancel out, and I have 100 divided by 2. So I end up with 50 watts. Does everybody see that? Please send me a chat or tell me if you want me to go through that again. Okay, so you guys got that. And when you give this to me, you do have to show your work, okay? I don't accept, oh, it's just C. Now you have to show your work. Okay, let's finish this worksheet up. I think we should be able to get this done. Okay, here we go. Number 13, let's see who's next here. Ralph, I got a 4 and a 6 ohm resistor connected in series, and the current is measured to be 4 amps. So can you describe to me, Ralph, as carefully as you can, how I should draw that?
So the 4 and the 6 amps should be on the same node.
Okay, not on the same node. They share one node, but they're in series. You know, you're more than welcome to, you know, use help from what you know things look like when they're in series versus what things look like when they're in parallel. In fact, this would work. Here's 2 resistors in series that have a current going through it. But if they have a current going through it, there has to be a power supply or a battery. So this would work. I didn't mean to tell you, but is that what you're going to tell me?
Yeah, that's what I meant. I don't know how to describe it though.
I know it's not easy right now. I would have had you come up to the board. Here's a way I'm going to draw it. Okay, I got some sort of battery, and I have this resistor, and I have this resistor. There we go. One is 4 ohms, and the other one is 6 ohms. There we go. That works, yeah? And they tell me that the current going through it, I, is 4 amps. Okay, so now, Ralph, what is the voltage drop across the 4 ohm resistor? How much voltage drops across this resistor? What is the equation for
2.
V? Equation for V is?
IR.
Good, IR. And just through this resistor, I know the current is 4 amps. And I know the resistor is 4 ohms. So how much voltage is going through the 4 ohm resistor?
6.
16? I think he meant 16 volts. Okay, good. 4 ohms. The 4 ohm resistor is 16 ohms. Good. Michelle, what about the next one, the 6 ohm resistor? How would you do the voltage across the 6 ohm resistor?
So it will be kind of the same. We'll use the same equation, right?
Muy bien. What do you have?
So V would equals 4A times 6 ohms.
Good. 4 amps times 6 ohms. And what do you get?
24.
Good. So tell me, how much voltage must this battery have? If this one has 16 volts right there, and this one has 24 volts, how much must be the battery?
Am I supposed to add them up?
Yes, ma'am. Muy bien. She did it. There you go. 40 volts. So that must be a big old power supply of 40 volts. Okay. So this guy here was 40 volts. And 16 of it is being used up by this 4 ohm resistor, and 24 volts is being used up by this resistor. Okay, muy bien, muy bien. Okay, let's see. We're down to Ashley. Ashley, I think I'm going to help you with this one. What's wrong with this circuit? Okay, so here's the thing you guys have to learn. I'm not going to make you do this, so I'll do the next one. When you're measuring voltage, a voltmeter, you can go across. What does that mean? That's what you guys did in the classroom. You took one lead of the voltmeter on one side and one on the other side. Not true if you're measuring current. The current has to be in series. Okay, the current, you got to stick it in series. You can't put this right here. It says A. That means it's an ammeter. You can't put it in parallel. Why? Anytime you put things in a parallel, the equivalent resistance is going to decrease. So now you've just changed the circuit. You can't do that. So if you're going to measure current, you have to break the circuit somewhere, maybe like between here and here, and put your ammeter there. Okay, so this is a way to learn that to measure voltage, yes, it's across, it's fine in parallel. But to measure current, you have to be in series. This configuration is in parallel. All right, let's finish up this worksheet. We're almost done here. Let's see. I'm going to give this one to Ashley. Why do we say voltage across or the voltage with respect to? Why can't we say voltage? Okay, here are our choices. Uh-oh, here comes another note from someone who keeps correcting me. I already told him that. Yeah, I already told him.
No, current.
All right. You guys, isn't that funny? He wants me to make sure. Current is through an element, but voltage is across. That's what I'm trying to explain. Oh my gosh. That's what happens when you're married to another electrical engineer. Okay. All right, so here we go. Why do we say voltage across or voltage with respect to? Why can't we just say voltage? And it's just the reason why he just popped his head in there. Voltage is a measure of electric potential between two electrical points. That should be between two electrical points. Somehow I lost the S. Okay, I just gave that to you. All right, so this one here, this last one, I'll start it for you, but we're running out of time here. So this one we have to draw a circuit for. Let me see, I gotta push the page up here. There we go. Push the page up. All right. The voltage across two resistors in series is 10 volts. All right. So that tells me I should draw two resistors in series, and then across each of them adds up to 10 volts. One resistor is twice as large as the other. What is the voltage across the larger resistor? And what is the voltage across the smaller resistor? Okay, so this is basically fun with math. Let me see, I'm going to draw a picture for you guys here. Okay, let's see, we'll draw a picture. All right, so the first one, I've got two resistors in series. Here's my R and my second one. I'm going to call one R and my other one 2R. You guys fine with that? It said that one of the resistors is twice as the other. So I'm going to call one R and the other one's 2R. And then they are combined, it's 10 volts. Their voltage across both of them. The voltage across here, VR plus the V across 2R equals 10 volts. We good? Everybody good with that? All right, so this is just gonna see how well do you understand what we're talking about here. Well, I told you guys that this guy, he doesn't know who's parallel, who's series, he doesn't care. He only sees one resistance. He only sees the equivalent resistance. So Ashley, what would I write here for the equivalent resistance? What's our equivalent?
Would your equivalent to that be, would it be 8?
Well, wait a minute. Remember resistors? Where's my summary sheet? Resistors, when they're in series, you just add them up. That's all you do.
Okay.
Okay? Resistors. So I've got 1R. I put a 1 because we're used to coefficients. 1R and a 2R. So what's our equivalent equal to?
Oh, would it be 3?
3R.
3R, yes.
Yes, 3R. So whatever R is, it's 3 times it. Okay, now what else do I know here? It wants to know what the current is in each one. Okay, it wants to know we want to know what the current. They're asking what's the current and it wants to know what the voltage is across the larger resistor. So what's this one right here? I'm going to call V of 2R, and it wants to know what the voltage across this one is. So let me ask you this. What's this voltage, V1R plus V2R equal to? V of the first one plus V of the 2R. What's that equal to, Ashley, when I add them up?
When you add them up, would that still be
10? 10. Yes. Okay. Because some of it gets used up here, some of it gets used up here. So that'll be 10 volts when you add them up. Okay. All right. So really, we're going to end up with 2 equations, 2 unknowns, but I'm going to go ahead and start right here. The current, I know that the current coming out of the battery, if V equals IR, then I is just V over R. And the V here is 10 volts and the R is 3 over R. So I've got 10 volts over 3R. So whatever R is, the current going through everybody here is just 10 over 3R. You guys with me? Yeah? Okay, so that's the current going there. I'm getting nervous about the time. I think you guys are up, all right? Let me see the time. Okay. I think I can't let you guys, I don't want to make you guys late to class. So I'll, you know what? I'll post this right now on Google Classroom. All right? So I'll stop share. You guys are good? I don't want to make you guys late. It's just math now, just fun with math. So I'll see you lunes. Have a good weekend. Let me know if you have any questions. Adios, adios. Bye-bye.